In this section we are going to add feedback to the op-amp. In the next couple of slides, we are briefly going to jump ahead and show that this model works as a non-inverting amplifier, with feedback. This is what the ideal, non-inverting amplifier looks like when we add feedback to it. There are two feedback resistors, RFB1 and RFB2. These two resistors act as a voltage divider, and feeds back a portion of the output to the negative input terminal of the op-amp. This is a non-inverting amplifier. The input signal is applied to the positive terminal of the op-amp. The feedback is applied to the negative terminal of the op-amp. This amplifier has a closed loop gain of 2, based on the values for RF1 and RFB2. The equation for the output voltage in terms of the input voltage and the closed loop gain factor is shown. The resistor divider network, formed by RFB1 and RFB2, divides the output by 2 and feeds it back into the negative input terminal of the op-amp. With the input voltage at 1 volt peak, the output voltage is 2 volts peak, because the closed loop gain factor is 2. The voltage at the negative terminal is therefore at 1 volt. The end result is that both input terminals are at 1 volt. In this slide we are going to illustrate one of the benefits of feedback, and that is that it minimizes the effect of op-amp open loop gain variation. Normally with an open loop op-amp, the output voltage varies just as much as the op gain. This is really not ideal and it is difficult to predict what exactly the output voltage is going to be, because we are not sure of the op-amp gain. Let's look at an example. We start with a non-inverting amplifier with feedback, and an open loop gain of 1 million or 120 decibel. The closed loop feedback is 2, as determined by the feedback resistors, RFB1 and RF2. This graph shows the input voltage in red, with a peak voltage of 1 volt. The output voltage has a peak twice that of the input voltage, which is 2 volts. The waveforms are in phase. If we reduce the op-amp open loop gain from 1 million by a factor of 100, to 10,000. If we were operating with an open loop op-amp, the output voltage would also drop by a factor of 100. But as we shall see, this does not happen when we apply feedback. This is the schematic for the non-inverting op-amp, with the gain reduced from 1 million to 10,000, a reduction by a factor of 100. And this is what the input voltages look like. The input voltage is the same as before, with a peak of 1 volt. The output voltage remains at peak of 2 volt, despite the drop in the op-amp gain by a factor of 100. We continue with the benefits of feedback. In this slide we are going to dig a bit deeper into the concept of infinite bandwidth. As we already mentioned, the concept of bandwidth and feedback are closely related. We use the example used in the previous slide, which is the non-inverting amplifier with an op-amp open loop gain of 10,000. As before, the input and output are in phase, and the input amplitude is 1 volt and output amplitude is 2 volt. If we use LT-spice to plot the frequency response of this amplifier, it is a flat line across the frequency spectrum. This is what is meant with infinite bandwidth. The amplitude of the output is not attenuated at all at any frequency. So far, we have assumed that the bandwidth of the op-amp is infinite. This means it amplifies sine waves of all frequencies, without a drop-off in the amplification. In other words, the op-amp gain does not vary with frequency. This is of course an ideal situation. In the real world the op-amp bandwidth is not infinite, but rather finite.